Alright, in the previous video I built a do-it-yourself version of a 4x attenuator, just like here, and put it under tests. For low frequencies it worked fine, but for higher frequencies the attenuation was higher than 4x, and also there was a noticeable phase shift. So today we are going to try to understand what happens and how to fix it. To answer this question, I created a circuit simulation. Here we have a voltage generator, and the voltage goes to a 1 mega ohm resistor, then 500 kilo ohm to ground, and also to account for the wires being close enough together going into the B and C connector, I added a 5 picofarad capacitor. On the oscilloscope side, as specified for Pico 2204A, the impedance is 1 mega ohm resistor in parallel with 15 picofarad capacitor. Now let's do the DC simulation for this circuit. Alright, the simulation has finished, and we have 1 volt being converted into 0.25 volts. So there we have a perfect 4x attenuation, no issues here. However, now we are going to proceed to the AC analysis, and it will run for a while and will show us the following. So we are starting at low frequencies at a good 250 millivolts, but about 31 kilohertz the voltage drops to 177 millivolts, which is 71% of the original voltage. And in 71% of the voltage in engineering lingo is -3 decibel point, and also called the bandwidth of the device. So our attenuator here is not only dropping the voltage by 4 times, but it also acts as a low-pass filter with a bandwidth of 31 kilohertz. And we can say that this may be good enough for your purposes. So you just need to say that you have an attenuator 4x with a 31 kilohertz bandwidth. However, we can also try to improve on the circuit and make its bandwidth higher, and it's not that hard to do. Let's return back to the circuit and put a 6.7 picofarad capacitor in parallel with that 1 mega ohm resistor. Now, if you run the DC simulation, the capacitor is not going to make any difference. So, as expected, we are going to have 0.25 volts at the output, not a problem. But when we go and do the AC analysis, what we are going to see, and this graph hides the magnitude of the change, it's actually very flat. We are starting with 250 millivolts, and for 31 kilohertz it's still 249.88, and going to 100 kilo ohm it's 249.8, and then going to 1 megahertz it's 249.8. So it really hasn't changed at all, and we basically fixed the issue that we had. Our bandwidth is perfect, and that's all because we added this 6.7 picofarad capacitor. Of course, the next question is, does it work in practice? So here, what I'm going to do, I'm going to take my original 4 4x attenuator, and then I'm going to add a 6.6 picofarad capacitor. I have two 3.3 picofarad capacitors, and I'm going to clip them in together and then touch the other end of the resistor, just like so, and see what happens. So, okay, let's go. Okay, so we saw that the square wave came out almost perfect, and so this is definitely a fix, adding this 6.6 picofarad capacitor. However, in real applications, sometimes a different way is used, and the reason for that is that the oscilloscope impedance can change from one device to another, or even from one channel to another on the same device. So this capacitor here may not be 15 picofarad, but maybe sometimes 13 picofarad or 17 picofarad, and such differences are going to have a big impact on whether the waveform is going to be distorted or not if you are using a fixed 6.6 value for this capacitor. So instead, what can be done is either make this capacitor adjustable, so we can take a screwdriver and change its value, or there is an alternative way where we can make this capacitor bigger, put it like 20 picofarad or more, and also add a bigger capacitor here in parallel with the 500 kilo ohm resistor. And what that would make is that the influence of changes in the oscilloscope capacitance are going to have a smaller effect because here we will have a big or bigger capacitor. So let's test out this idea. In this simulation, I have a 20 picofarad capacitor in parallel with the 1 mega ohm resistor, and in parallel with 500 kilo ohm resistor, I have a 45 picofarad capacitor, possibly variable, so that it can be adjusted with a screwdriver. Let's do the DC analysis for it first, and confirm that 1 volt becomes 0.25 for a DC voltage. Okay, that's good. Now let's do the AC analysis. And again, in this graph, the scale is hiding how flat the curve is. But here we start at 250 millivolts, and no matter what the frequency is, whether it's 100 kilohertz or 1 megahertz, our voltage is 249.7 millivolts. So it confirms that the attenuation of 4 times happens for all the frequencies that we care about. Okay, so we have confirmed that this circuit works as well, and it works well even if the value of this capacitor inside the oscilloscope changes a little bit, because it's going to be small compared to the value of the capacitor here that we added. And does this work in practice? Is it used in practice? And the answer is yes. What I'm going to do is I'm going to tear down a Hantek 20X attenuator and see what's inside. So here I have a Hantek HT201 attenuator disassembled. After removing 2 clips from the BNC connectors, we can pry the cover off. And what we see here, let's zoom in. In the circuit board we have the input, and we have a 1 mega ohm resistor and a capacitor in parallel with it. And going to ground, we have a 56 kilo ohm resistor and 2 capacitors in parallel with it, providing the necessary capacitance to provide the proper attenuation, not only for the low frequencies but also for high frequencies. And they actually claim that the bandwidth of this device is 10 megahertz, though I haven't checked that. But in general, this circuit matches what we came up with. Also note that the circuit board is enclosed in a metal box that keeps out all electromagnetic interference out. So this is important. Even though 3D printing plastic enclosure is kind of fun, it's no match for the metal box for keeping out all the noise.